Good afternoon, all. This is Dr. Bankole Ujo Olufunso Samuel, and I'll be taking this class on CHM 406-411, that is reaction kinetics. So we are going to be looking at some questions and their respective solutions. Now let's start with question 1. Explain why a reaction between two complex nonlinear molecules like CH4 and Cl2 might have a very low steric factor. Draw a simple sketch of a productive versus non-productive collision between them. So to solve this is just telling what are the factors that can negatively impact effective collisions between two molecules. Because for two reactant molecules to collide and then give rise to the product, okay, the first thing that must happen there is they must collide in such a way that both of their potential energies increase, and the collision must be in such a way that it is in the right orientation. So what are the factors that can affect this from happening? One, the specific reactive site. So now looking at chlorine gas and methane. So the attacking chlorine atom must target a specific CH bond. Collisions elsewhere on the CH4 tetrahedron are non-productive. So it is between the C, okay, the carbon, right? There's a particular carbon hydrogen bond that must combine with the chlorine atom. Then number 2, transition state geometry. So the chlorine must approach that CH bond along the right axis. Okay, they must approach along the right axis before they can properly collide and then form a bond. That's the second one. The third one, okay, the chlorine must overcome any spatial hindrance. Spatial hindrance, for instance, might be other CH bonds on methane. So it must overcome it to form a bond. Now to the second part of the question, draw a simple sketch of a productive versus non-productive collision. So the first one here you have is productive collision, where you see the arrow comes from the carbon to the two chlorine atoms. But this is non-productive because the arrow is coming from the hydrogen to the two chlorine atoms, so they cannot bind, so this is non-productive. Okay, now to question 2. Sketch a reaction coordinate diagram for an endothermic reaction. Label the axis, then label the axis EA, delta H, and the activated complex. Explain how adding a catalyst would change this diagram and what feature would not change. So the first thing you need to do is to sketch the reaction coordinate diagram for an endothermic reaction. So you first of all you put your reactant here, then you draw the curve, okay, and then you get your products. Take note, the product side is higher than the reactant side. Why? Because it is endothermic. Okay, so the potential energy of the product is higher than that of the reactant. Now to the second part, it said label the axis. So the axis here is potential energy, here is reaction coordinate, and EA. So please, this is where there's a slight correction here. EA starts from the top of the curve down to the line where you have the reactant. So from here to here you draw the arrow, that is EA. Okay, delta H is what you have between the product and the reactant, so that's delta H. And the activated complex, so there you have the activated complex. So the second part of that question has been answered. Now to the third part. What will happen when you add a catalyst to this diagram? So all I need you to do is just to put this down. Okay, you can see lower activation energy. Okay, that's the most important thing I need you to outline when answering this question. Okay, then the fourth part of this question said, what feature will not change? The feature that will not change is the energy level. So we have the energy levels of the reactants and the products will remain unchanged. Also, delta H, which is enthalpy change of the reaction, will remain unchanged by the catalyst. So that's it. So you've answered that. Now to the third question here, how can you answer it? The bimolecular reaction 2NOCl giving 2NO plus Cl2 has a rate constant of 2 times 10 raised power minus 5 liter per mole per second at 300 Kelvin and 7 times 10 raised power minus 3 liter per mole per second at 400 Kelvin. Calculate the activation energy for this reaction. So how can you go about this? So use what is called the 2-point form of the Arrhenius equation. This is it here. Okay, so link K2 over K1 is equals to EA over R, then open bracket 1 over T1 minus 1 over T2, you close the bracket. Now K1 and K2 has been given, T1 and T2 has been given, then you have R as 8.314. So to solve it in a very simple format, you can first of all get your link K2 over K1. So link K2 over K1, so you start with K2 over K1, you get 350, and then you get the link which makes it 5 point, you can see there 5.8579. So you've gotten the value for that. Now you can get the value for what is in this bracket here. So that is 1 over T1 minus 1 over T2. That's 1 over 300 minus 1 over 400, and then you get this. You get 1 over 1200 times, so which is equals to 8.333 times 10 power minus 4 per Kelvin. Okay. Now to solve for E over R, okay, so you make it link K2 over K1 is equals to 1 over T1 minus 1 over T2, and that will be equal to 5.8579 over 1 over 1200. So that will give you 7029.5. Okay, so that's what you have here as EA over R. So to get your EA, which is what you are looking for, so EA is equals to 7029.5 times 8.314. Remember that is our R, 8.314. When you multiply, you get this, okay, 58440 joules per mole, which you can convert to, if you wish to, for 58.44 kilojoules per mole. Okay, so that is your EA, activation energy. Now to week 2, here we'll be looking at unimolecular and bimolecular reactions. So the first question here goes thus: explain the apparent paradox in a unimolecular reaction. How does the Lindemann-Hinshelwood mechanism solve this paradox? Use the Jenga tower or party hype analogy in your explanation. Okay, so the first thing is telling you to do, you have the several parts. So for all my questions, kindly take note that in one question you have several parts. Okay, so take your time, sort out all the parts, and then answer them one by one. Now explain, the first part is explain the paradox. Okay, the second part is how the Lindemann-Hinshelwood solve this paradox, and the third part is the party hype analogy. So let's look at the paradox itself. So the paradox is simply saying, okay, molecules must collide for reactions to happen. Okay, but if this is true, then that means it must be what? The process must be bimolecular, involving two molecules. But the problem is that we have some that we call them unimolecular. So how come are they unimolecular if you are going to require two molecules to collide for reaction to proceed? So that is what this is saying. Okay, so you can simply write this down and you get your full marks. Now to the second part, how does the Lindemann-Hinshelwood mechanism resolve this paradox? So all you need to do is to give me, first of all, the equations for Lindemann-Hinshelwood mechanism, which I gave in class earlier on. So, but here are they. So you can see the first one is A combining with A to give activated A and non-activated A, right? Then the next one is the reversible reaction, that's the activation, which is activated A combining with A to give A plus A. The third one, which I termed the redetermining step, is A activated A giving rise to product. So these are possibilities that you can get. So once you put down these three equations, all you now need to do is just to talk about how it is resolved, and this statement is okay. The key is that the formation of A as A asterisk or activated A is bimolecular, but the uh, rate determining step, okay, you can put that, but the rate determining step is unimolecular. So I think that would be a better way to put it. So rate determining step is unimolecular. So that's fine. Okay. Now to the party hype. That's the last part of that question. Party hype. What do you mean by party hype? So party hype is also talking about these three equations. Okay. So the first equation where we have activation, you can put it as a quiet person getting hyped, okay, only by interacting with another person that's in a party. Okay, so some people get hyped when they interact with others, but you can also have the activation. A hyped person might bump into a quiet person and calm down. So this can also happen in a party scenario. Okay, so you can have somebody that will just dull your spirit, and that will be it. Then the third one, okay, where it gives the product is if a hyped person stays hyped long enough, they spontaneously start dancing. So then you have the formation of products. So that's the party hype analogy. Okay, now to our next question. The unimolecular decomposition of cyclopropane, we have A given products follow the Lindemann-Hinshelwood mechanism. At a certain low pressure, the observed half-life is 2 seconds, where A is 1 times 10 raised to power minus 3 molar, and 1 second when concentration of A is 2 times 10 raised to power minus 3 molar. Explain this change and determine the observed reaction order at this pressure. So this is quite straightforward. Okay, we want to explain the change and determine the reaction order, that's order of reaction. Okay, whether it's first order, zero order, second order, or third order. So that's what we want to check. Now, how can you approach this? So remember I did something like this I've got something like this in class using steady state approximation. Can you remember? So you can look at my pointer here. So here it is. So this is what we derived in class, okay, from the Lindemann-Hinshelwood mechanism using steady state approximation. Okay, now if this is true, then we can, so this is true for just a normal condition, but the question said at low pressure. So what makes low pressure different? So at low pressure, the collision frequency is low. That means K2 is far greater than K minus 1A. So K2 is far greater than K minus 1A. So we can as well, that means K minus 1A is negligible. We can as well just rule it out. So what we can do here is to cancel this K minus 1A, okay? So we cancel it. And then what are we left with? We are left with K1, K2, A square over K2. And so what do we get? K2 cancels K2, right? And so we are left with K1 A square. And so that is what you get here. Can you see it? Okay, so that's what you get here. Can see it. So from this, what can we say about the order from your knowledge about order of reaction? So the order is what? It's second order. Why? Because you have of this square, right? So the exponential. So what it is raised to the power. So it's raised to the power of 2. So that's what you have here. So it's second order, right? Now you can put it down. Okay, so it is second order reaction. So all you now need to do, the reason why you are giving these values is just to confirm for us, okay, the order, and to be able to explain the change. So let's explain the change looking at what you have here. If you look at the change you have here, you will notice that when the half-life is 2 seconds, concentration is 1, half-life is 1 second, concentration increases double fold. So that means as you reduce the concentration, as you reduce the half-life, the concentration increases. And this is typical of a second order reaction, okay? So, and here you can see it. So T half is equals to 1 over K, so then A naught, okay? And so what you can see is that this confirms the inverse relationship, okay? So half-life increases, or you can say half-life is inversely proportional to the initial concentration as seen above. I think that would be a good explanation. That's all. Okay, so you can answer it that way too. Now to question 3 in this section. Here we'll be looking at, for a unimolecular reaction at very low pressure, the observed rate law is rate equals K A square. Now, which step in the Lindemann-Hinshelwood mechanism is rate determining under these conditions, and why? So what it's telling is that if the rate is Ka square, okay, so which step is the rate determining under this condition? So this is just similar to what we have done before, okay? So we know even from what has been done in the previous question that at very low pressure, so you said which step is the rate determining. So we know that for you to get R is equals to K square, the first that first step, which is the bimolecular activation step, becomes the rate determining step, okay? So when that is the rate determining step, okay, so it becomes what? It becomes second order, right? Now say why, so and why. Okay, that's the question. And why? So why is this happening? Why does it happen that way? One, at low pressure there's low collision frequency. That's one. Two, okay, at low pressure the deactivation step is slower than the activation step. So that's it. So that is how to answer this question. Okay, so I'll stop here for now, and then we'll consider the other part later. Okay.